Let's thank the presenter.
Okay. So hello, everyone. I'm the proxy presenter of this paper. So if you have any questions, you can send email to these authors. And this paper is titled Knowledge-Based Multiple Adaptive Spaces Fusion for Recommendation. As you can see, the report outlines contains the following 5 parts. So, as we all know, recommendation algorithms based on knowledge graphs remain a hot topic in today's recommendation community. Recently, there has been an influx of KG-enhanced recommendation method, including some famous works such as KGCL, CGKR, KGAT, and others. However, we have identified certain limitations in these existing KG-based algorithms. Specifically, existing KG-enhanced recommender systems have primarily been designed based on Euclidean space, neglecting the considerations of curvature. Recent studies, however, has revealed that vast graph structured data exhibits highly non-Euclidean properties. As illustrated on the right, hyperbolic space is more suitable for modeling tree structures, while spherical space is more appropriate for modeling ring structures. On the other hand, existing non-Euclidean recommendation methods have the following issues. First, existing non-Euclidean methods treat the K as a trainable parameter, but model parameters constraints depend on the changes of curvature. Once the curvature varies, the internal structure of a manifold may be destroyed, and the user unable to obtain high-quality embeddings. The second, existing mixed curvature method directly operate on various manifolds without considering the heterogeneity. For instance, the global distance computation just sum up the distance without distinguishing the importance of various manifolds. Motivated by the aforementioned issues, we have proposed this work, and its contributors can be summarized in the following 3 points. First, unlike existing methods that solely adopted a specific manifold, we introduced the unified space is compatible with the hyperbolic, Euclidean, and spherical spaces. Second, we propose a geometric-aware optimization strategy which enables the pull and push processors benefited from both hyperbolical and spherical spaces. Third, to break the limitation of the single space expression ability, we further integrate multiple unified spaces to more accurately capture the structural information on a global level. And you can refer to this page where the preliminary knowledge introduces some basic operations from the joint space. Next, we introduce our proposed method, MCKG. This figure shows the overall structure of MCKG, which consists of 3 parts. First, the overall process of high-order information extraction based on the single adaptive space. Second, aggregating the subspace embeddings and adopt an attention mechanism to calculate the global distance. Third, the proposed optimization strategy enables the pull and push processors to be geometric aware in both hyperbolic and spherical spaces. High-order information extraction consists of the following 4 steps. First, encoding the initial Euclidean embeddings onto the unified space. Second, rational attention function. Third, the embeddings of aggregate neighbors to update its own embedding. Fourth, combining the embeddings at each layer. Now we further consider a sequence of manifold. The global distance is the weighted sum of distances in each subspace. Second, the embeddings of multiple unified spaces. And third, the weight parameters are defined as follows. When entities x and y progressively moves away from the origin in hyperbolic space, the ratio becomes smaller. First, in hyperbolic spaces, the space capacity of the area near the origin is extremely narrow. Thus, a smaller margin is beneficial to distinguish highly similar entities. While in areas far away from the origin, we prefer a greater margin because the room is spacious enough. Second, in spherical spaces, the origin area is relatively spacious, but the boundary area is narrow. Therefore, we expect assigning larger margins to the area closer to the spherical origin, and smaller margins to the area farther from the spherical origin. This picture shows that the performance compared with other computing methods on the 3 datasets with latent dimension ranging from 2 to 32. And we summarize the overall comparison among all computing models in this table. We have the following conclusions. First, Euclidean methods are easily impacted by the embedding size, while hyperbolic methods still perform well even in low dimensions. Second, compared with other competitive models, MCKG performs best in most cases. Roughly speaking, this is attributed to our model's ability of adaptive curvature learning and geometry. We also summarize the comparison of performance among different variants in this table, and we found that all aggregators adopting geometry-aware margins are significantly better than other margins, and the margin performance in HICF is not even as good as a constant margin. Second, the choice of aggregators is still important, and the margin we design will significantly improve the model performance, especially in larger datasets, for example, the book crossing. As you can see, we also conducted other ablation experiments, such as the impact of different layers of manifolds and different depths of aggregation on the model. Finally, we conducted interesting embedding visualization experiments. In the accompanying picture, nodes of different colors represent popular trains among the atoms. It is evident that after joint spatial aggregation, there have been some interesting changes in entity representation. First, in moving length 1 million, we can clearly see that unpopular atoms, that is the purple points, are pushed out at the both ends, while the popular atoms, that is the green and yellow points, are pulled in the middle region. Second, in the last FM and book crossing, we hardly see a clear difference between the trained atom embeddings and the original embeddings, but this way may be more beneficial for the recommendation's fairness. Generally speaking, we summarize this work into the following 3 points. First, to the best of our knowledge, this is the first work to apply multiple adaptive spaces fusion for knowledge-enhanced recommender systems. Second, we present a knowledge-based multiple adaptive spaces fusion method for recommendation. To obtain the high-quality embeddings for recommendation, we introduce the unified space to describe the complex structures of KG, then further fuse multiple subspaces in an attention manner. And third, finally, our proposed geometric-aware optimization strategy is the first work that considers the properties of both hyperbolic and spherical spaces. And thank you for your listening. My presentation ends here.
Thank you, Zhenzhe, for your presentation.